Right. Right. So first of all, thank you for the organizer for inviting me to do this presentation. And so today I'm going to talk about the energetic particle transport induced by macroscopic modes in tokamak plasma. So this work has been done jointly with all of the people highlighted here below that are from the University of California in Irvine, the Chinese Academy of Sciences, PBPL, Oak Ridge, and the ITER organization. So as I know that not all of you are familiar with fast particles or isotokamak plasma, I'm just going to start with a few slides explaining, first of all, what are energetic particles. Okay, all right, so in tokamak plasma, so usually the majority species that we also call the bulk plasma are at temperature of order 10 million to 150 million degrees, which is like 2 to 20 keV. But like on top of these bulk plasma, we also have what we call subatomic particles, or also energetic particles that are 10 to 100 times higher in temperature. So like those fast particles results either from non-inductive heating technique, such as the neutral beam injector that we have here, for example, in ITER, or like the ion cyclotron resonance heating. And they also can arise from nuclear fission reactions, such as the alpha particles. So we also have some kind of fast electrons in the system, but like those are beyond the scope of my talk here. So the purpose of such fast particles actually is to either initiate the reaction through like using the heating techniques, or to maintain the plasma heat by transferring the kinetic energy of fast particles up to the bulk plasma to the collisions. And so like in order to be able to do steady state operations, so like the confinement of such fast particles is very critical. But as you can expect, so like things are not as easy. And in tokamaks, we do have what we call EP transport. So I'm going to refer as EP now for the energetic particles. So like we can have EP transport in the alpha direction, so from inside to outside the tokamak. And so like those can, first of all, as I said, degrade the energy balance, also the overall confinement of the device, and also threaten the device integrity, since sometimes the fast particles can hit the walls and degrade it. So in order to come up with mitigation strategies, we first need to be able to realistically predict such transport. But like the other tricky thing is that such a transport can arise at a very different scales. So ZP transport is two instabilities that arise here at different spatial and temporal scales, ranging from microscopic scale with macroturbulence to mesoscopic with all of the ion modes, and to macroscopic. So here you have example of such instabilities in the ITER tokamak. So we have done simulation showing each of them. So here at the macroscopic scale, so that's what we call IN mode. So you have, for example, the trapped electron node here that creates very, very fine scale. Then you have the reverse shear Alvan mode, so that produces some kind of mesoscopic scale. And finally, the macroscopic scale, for example, here, a fishbone, which is going to be the main stability that I'm going to discuss in that talk. So before discussing what kind of formalism we use to do such a prediction, we first need to, I first need to give a few words on how fast particles behave in tokamaks and what are the trajectories. So this is a typical trajectory of a trap particle in tokamaks. So in tokamaks, we have two types of particles, so trapped and passing, which is due to the presence of finite gradient of B field from outside the torus to inside. And so when the parallel velocity of the particles is not high enough, so like they get trapped in this banana-like shape here, and otherwise they are passing, so meaning that they go through the toroidal direction without any constraint. So at equilibrium, meaning without any kind of instability, so we can observe that we have three different kinds of motion of particles that are linked to three different frequencies. So you have the energy, the magnetic momentum, and the total momentum, link this one here to the axis-symmetric configuration of the tokamak. And so like here you have the different frequencies. So the first one, the gyro frequency, is so large that it cannot interact with any of the ones in the tokamak. So we don't quite care about this one. But actually, the other frequency, like the bounce transit frequency in here, or the positional frequency, which is the slow drift here of the particles, are the frequency of order 10 to the 4, 10 to the 5 hertz, which is about the same order of magnitude as most of the instabilities I discussed the slide before. So in order to be able to do a prediction, then our formalism needs to have a kinetic treatment, both to take into account the wave particle resonance that can exist, and also because the size of the orbits here of particles are sometimes much bigger than the size of the modes that are discussed. So let's now discuss the different formalisms that we can use. So there are two types of those. So like that's what we call the first principle simulation. So the first formalism is a gyrokinetic one, and the other one is a kinetic MHD. So MHD standing for magneto hydrodynamics. So I'm going to explain those formalism in a non-exhaustive way in the next slide. So typically, the kinetic MHD codes were historically used to describe macroscopic fluid kinetic instabilities, while gyrokinetic ones were used for macroscopic modes through the study of macroturbulence. But in recent years, both those formalism were used to verify and validate simulation for mesoscopic modes. So here you have an example of verification. So a verification is basically a benchmark between different codes to ensure that all of those codes are able to simulate accurately the instability. And the validation is a comparison between simulation results and experimental measurements. So here, for example, we look at the reverse shear Alvan-Hagen mode. And so we compare here between different gyrokinetic and kinetic MHD codes, the growth rate of the mode and the frequency against different toroidal moment levels. So, but in order to be able to have realistic EP transfer prediction, we need to incorporate all of those different scales, so macroscopic, mesoscopic, and macroscopic on equal fooling, because all of those different instabilities can interact with each other to generate a new kind of EP transfer. So the VNV that was carried out here for the mesoscopic mode needs them to be generalized for all kinds of modes, so that we can end up with a formalism that can treat everything. For example, we can allow gyrokinetic codes to simulate accurately macroscopic MHD modes. So now let me give you a few words in a non-exhaustive way on what are the gyrokinetic and kinetic MHD formalism. So the gyrokinetic formalism, the historical approach is to use a Maxwell equation for the particle species and a Poisson equation. So adopting that approach is a purely electrostatic model that retains 5D phase space dynamics. So 5D, not 6, because we neglect the gyro frequency of particles. But we can enhance this formalism by taking into account parallel and perpendicular Ampere equation, so that we can include magnetic fluctuation that are mandatory if one wants to be able to look at macroscopic MHD modes. So on the other side, you have the kinetic MHD mode formalism. Sorry. So originally, it was a purely fluid model that was just taking the moments of this Maxwell equation by using this infinity equation, momentum, and finally an energy equation, this Maxwell equation. So here we have a given closure. And so, like, since we have saw that to predict the EP transport, we need to have some kind of kinetic approach. So, like in recent years, those codes actually included the kinetic approach by using Lorentz equation to describe in 6D, for example, the trajectories of fast particles, and to have a coupling into the immediate equation by taking into account here the divergence of the particle tensor pressure tensor here. So those two formalism can simulate accurately, realistically the transport. But in this talk, we're going to mainly focus about the gyrokinetic formalism and how we can, in the first part, treat MHD. So the code I'm using is the global gyrokinetic code GTC that has been in the past used, verified, and validated for both macroturbulence and AEs. And very recently, the code capability at simulating MHD was demonstrated for the N=1 kink mode through a verification and validation using discrete experiments. So I'm going to talk about that in the first part. And then with this new MHD capability, we have applied the code to study the EP transport induced by the Fishbone instability in both D3D and interplasma as a stepping stone, actually towards the upcoming pro-scale simulation that we are currently conducting. So as an example here, you have a Fishbone node in either, so simulated with the GTC code. So here I'm putting the electrostatic potential. So before entering all of those details, I need first to explain what is both of those instabilities, the kink and the Fishbone. So the kink mode is essentially a fluid instability that occurs at the plasma core. So here you can see the electron temperature in a tokamak during kink instability. So you can see that you have a mode pushing the plasma towards a given resonance surface here. So this resonance surface is identified this way. So you have the toroidal direction in that direction and toroidal here. And so associated to that direction, you have a mode number. So N are for toroidal mode number and N are for toroidal ones. So so this surface is defined when the safety factor here is equal to this fraction between toroidal and toroidal mode number. And Q here is what we call the safety factor, which is actually a measurement of the elasticity of the plasma. So the number of toroidal turn a field line takes when it does one periodal turn. So usually in tokamak, the most unstable one, unstable kink mode is the n=1 mode with a typical frequency of 10 to the 4 hertz. And experimentally, this is problematic because it can create what we call a sawtooth crash. So as the pressure builds up due to the push here, you can have magnetic connection that will release all of the temperature and pressure out in the plasma. So that's what you can see here. Here you have a kink growing that is pressuring the core plasma. And you're going to have a large recognition that will drop the temperature. That's what we call a sawtooth crash. And so also for those modes, the kinetic approach is relevant because during those events, reconnection, so you have a very fine scale current sheets that are much smaller than the particle orbits. So that's why it's also useful to do a gyrokinetic simulation for that. And then we have the Fishbone mode. So the Fishbone mode is an instability that is fully stabilized by fast particles past a threshold in pressure. So this one has the same structure as a kink, and is destabilized through resonant interaction between the mode frequency and the precessional or bound frequencies of fast particles. So experimentally, you can see it here. For example, you have the time evolution of the time derivative of the periodal field. You have this kind of burst here that looks like a fishbone. That's why we call it that way. And together with this burst, we can see that we have a huge drop here in the Newton emission. Actually, this is due to fast particle transport. So because when the particles are interacting with the mode, they give away energy to the mode and get transported in order to preserve here this non-adiabatic invariance. And together with that, we also have a downshaping of the mode frequency. Right. So now that I've introduced those instabilities, is the outline of my talk. So in the first part, I'm going to discuss the verification and validation of fluid simulation. So that was recently published in nuclear fusion. And then I'm going to discuss the GT simulation of the fusion-induced TP transport. So first, starting with the verification, so meaning the benchmark between different codes. So we have chosen 5 different codes. So one is a gyrokinetic type, GTC. And all of the others are kinetic imaging types, so GAM solver, GTC1, NovaK, and NixTorK. So all of those codes have a free model, so essentially they are capable at using stability. And all of those codes can incorporate various types, as you can see here, of ion kinetic effects. But GTC is the only one that can, on top of that, include also kinetic response for electrons. So GTC uses a multi-level physics model that ranges from the fully gyrokinetic one for both ion to electron up to the one free diagonal image G limit. So now let's describe the discharge that we have used to conduct this D&D work. So we have selected this discharge here that features an equivalent Higgs mode. And we have reproduced the magnetic configuration from that discharge using the IFIT code based on experimental measurements. So here you can see the different flux surfaces in the periodal plan between different codes. So the issue is that all of the code of our benchmark can't take IFIT as the input for the simulation. So we have to recreate all of those equilibrium using the cheese code and then make sure that they were identical to the IFIT output. So that's what we did here. So you can see the Q=1 to Q=4 flux surface in the different code and IFIT, and you can see that they are very identical. Also, you can see the different pressure profile and Q profile between the different codes and IFIT. They are also identical, and having those 3 identical means that the MHD equilibrium described in all of the codes are the same, which is actually very critical to conduct a benchmark for the kink instability, given that the mode is very sensitive to any change in either pressure or Q profiles. Now let's go on with the benchmark itself. So to conduct the benchmark, we have done ideal MHD simulation, doing a beta scan, so scanning up the on-axis pressure of the total pressure. So you can see here the growth rate of the instability between different codes, and as you can see here, we have obtained an excellent quantitative agreement between both gyrokinetic and MHD formalism, showing that gyrokinetic codes can accurately simulate MHD as well. So in obtaining this result with the gyrokinetic code, so 2 ingredients were physically mandatory to obtain it. So first was the inclusion of finite delta B parallel fluctuation, so meaning that we cannot do this simulation in reduced MHD because otherwise the mode is fully stable, which is consistent actually with some recent analytical theory. And the other ingredient was that the equilibrium current that was used in GTC needed to exactly satisfy the Brochard equation in order to obtain a valid agreement. So now that we have done the verification, I'm going to turn to the validation. So here we are comparing the delta TE profile is obtained between GTC simulation and XOR, so in blue GTC and red XOR, with the ECE measurement that measures delta T in the experiment. So as you can, so like here we measure it against the major radius of the tokamak. So as you can see, we obtain a very good agreement from this linear simulation on the high field side. Slightly less good one for the low field side, but in general we find that we have a reasonable agreement that provides a linear validation. It's only linear because we did not compare the saturation amplitude, so we need to perform nonlinear simulation for that to complete it. So that's currently being done. And we have some preliminary results that show actually that the inclusion of kinetic thermal ion decreased significantly the saturation amplitude compared to ideal MHD or resistive MHD. Yes.
What is the unit for the electron temperature fluctuation?
Exactly. So like those are actually linear simulations. So here everything is normalized. So I'm only comparing the profile shape. But I will conduct a nonlinear validation later. I will show you. All right. So so before finishing off this skill VNV, I'm just going to want to see how gyrokinetic formalism and kinetic MHD1 compare when we start adding kinetic effects for thermal ion. So to do that, so we have included the thermal ion with a given pressure profile here, as you can see, and we have made sure that the total pressure is unchanged for all cases by using a P profile, so that the total pressure is still the same. So yeah, we have done a TI scan for the mode burst rate between M2DC1, XRK, and GTC. So we can see that in blue and red, so the kinetic MHD code actually agree with each other when we start increasing the ion temperature, meaning that we have a stabilization of the kinetic stability, when actually for GTC we don't. Actually, we have an increase here, which means that we have an additional drive. And so in order to be able to identify it, we have used a flat TI profile in GTC. Actually, using that, we are able to see that the results agree qualitatively now that we have a decrease. And it's also reasonable quantitative agreement is not that far away. So what means that the thermal ion temperature gradient brings an additional ITG type of drive to the simulation. And it means that the drift drive and finitely parallel physics are also necessary to capture fully the MHD dynamics as the MHD mode dynamics. All right. So now that we have discussed the MHD capability of GTC, so we can go on to the transport of macroscopic modes. So first, we're going to discuss the non-linear validation of the code using discrete experiment for the fishbone. So why do we want to study this transport with GTC? Because this study is part of an analysis of ITER scenarios that is done at the ITK group, that is an expert group of people working for ITER in the energetic particle department. And also this is also an activity funded by the US DOE. So we have 15 different codes in Europe, US, and Asia, looking at the transport for all of the different scales. But here we are going to focus mainly about the fishbone. So for the fishbone, ITER has given us a baseline coefficient scenario to conduct our simulation. So you can see here the Q profile is very flat, just above 1. Here you have the different partial pressure. In black, the total pressure. In green, you have the beam and the eye pressure, which is the only EP species here because we don't have a fusion reaction of few. So this scenario was found ideal MHD stable by ITER, but like in the ideal MHD limit. So we do need to include the ion kinetic effects also to extend this stability work. So to do that, so we have been given a distribution by the Astra code, the energy B-parallel space here, average over the entire torus, to be simple. And so we have tried to reproduce such a distribution in GTC by using a co-passing anisotropic slowing down PDF, as you can see here, preserving the local phase space gradient. So, but the issue with ITER is that it's not yet up and running. And before we can do any kind of prediction that are realistic, we first need to be able to validate our code against an existing discharge. So for that, we have selected a DCD shot, similar to the experiment in terms of similar Q profiles, profile shape and beta n. So here you can see the different safety factors. When you red, you have ITER, in blue, DCD. And here's the profile shapes. So for that discharge, actually, we did observe an equal one fishbone mode with frequency of order 20 kilohertz. And we would produce the PDF from the experiment using the new beam code in the same free space here. So again, we have used in GTC an anisotropic slowing down PDF to be able to study this mode. So now let's turn to the inner stability of that configuration. So actually using only maximum distribution for fast particles, we didn't find any low end modes unstable. But as soon as we use a realistic beam, we're able to find any common field mode destabilized past pressure, past a given density for fast particles. So you can see here in red the mode frequency and blue the growth rate. So past a given threshold, we obtain a mode. So here you can see the mode structure in the parallel plan for the electrostatic potential. So it's a dominant m equal 1, you can see here. But we also have a m equal 2 side then that actually extends the mode structure from the axis close to the edge. So now we also need to understand what kind of resonance is driving the mode. For that purpose, I'm going to introduce a phase space diagram that I'm going to use throughout the entire presentation. So I'm using event of motion phase space diagram. So P zeta and pitch angle. Wait, you can see here the pitch angle. So these are taken at a constant mu, which is important because it's a nonlinear event of motion. So here you can see the distribution in that phase space diagram. So in red you have the envelope, and so here you are on the top you have the trap section of the trap phase space here, and the passing one here. And you can see that you have two resonances that driving the mode that highlighted here in the different lines. So we obtain them by looking at the squared, the perturbed square distribution of fast particles. So you can see here a resonance for trap particles that is of a bounce precessional type. And you can see here also for passing particle a resonance of transit type. Yeah. So, but we can also see that the resonant contribution from passing particle is dominant, and it will mostly drive the mode. So now let's see how this kind of mode saturates in the nonlinear phase. So to do that, we have conducted a set of n equal 1 simulation with GTC with and without zonal flow contribution, which is a n equal 0 mode. So as you can see here in blue, you can see the time evolution of the electrostatic amplitude with n equal 1 only in blue, so it saturates at a given point. But we can see that when we start including zonal flow, so in red here for n equal 1, we have a much lower saturation amplitude. And here in black, you have the time evolution of the zonal flow itself that is has a growth rate of twice the n equal 1 mode due to the wave interaction. So yeah, so like the saturation for without zonal flow is about delta B over B 8 10 to the minus 3, which is significant, but it can lower by a factor of 4 when using zonal flow. Here I'm showing the radial electric field associated with the zonal flow. You can see that it's mostly negative picture here that peaks at the cumin surface in red here. And we also observed at saturation that for both cases that we have a decrease of the mode frequency, what we call a downshaping, so with and without zonal flow. So now you may wonder, so well, what is causing the mode here to saturate? So what causes this saturation is obviously the transport of fast particles. So here I'm showing the result of the simulation without zonal flow. So here in blue you have the density profile of fast particles before the fission burst, and in red after the fission burst. So you can see that you lose inside the cumin volume about 6% of the particles that are redistributed outside cumin. But with zonal flow, actually, you can see that this transport is reduced by a factor of 10, so only 0.6. And here I'm showing the fast particle energy flux as a function here of the radial profile, and here in function of time. So you can see that as the mode interacts with the particles, the particles are giving a ray energy to the mode, so it's negative here flux. And so they give you energy ray as they move outward. So that's what's going on. So now we want to have some idea how the saturation amplitude compare between the experiment and the simulation. So to do that, we have compared here the amplitude in electron volt of delta T profile. So on the left, you have simulation without zonal flow, and on the right, you have simulation with zonal flow. So in blue and green, you have the XOR K and GTC simulation on n equal 1. So you can see that they saturate at amplitude relatively similar, 500 to 600 electron volts. You can also see that, so here I'm showing the envelope. So you can see that also like GTC has a significant m equal 2 harmonic here that extends the structure. But so those saturation amplitude are much higher than the one from the EC measurement from the experiments. But we can see that as soon as we include zonal flow, we have much lower saturation amplitude with both MCDC1 and GTC simulation. Actually, like the m equal 2 feature of GTC simulation enables us to have a very good agreement, a quantitative one, with the experiments that provide us with a nonlinear validation for fission simulation. So now we might wonder, well, what is causing actually the zonal flow to reduce that much the saturation amplitude? So to do that, we look at the time evolution of the instantaneous transport in phase space. So that basically the time derivative of the Brochard distribution. So without zonal flow on the left and with zonal flow. So I'm going to show a video from the end of the linear phase to the middle of the non-linear phase. So you can see that as the mode is beginning to, yes, okay. As the mode is beginning to saturate, so you have a formation of one-in clumps. So you have a formation of one-in clumps, so positive and negative across the resonance for both the passing and the top resonance for the two cases. But as the simulation goes on, actually, you're going to start seeing some differences between the case with and without zonal flow. So usually it's here. Right, okay. So you can see actually that the passing resonance starts to die out much quicker in simulation with zonal flow, while it's still significant here for that case. And you can also see that without zonal flow, the one-in clump associated to the trap resonance is starting to drift away to larger psi position, which is totally normal because the mode is downshifting. So here, the one-in clump is just following the resonance being moved in that direction. But what actually with zonal flow, the one-in clump doesn't move at all. And this is even more, you can see it even better if I go on in the simulation. So you have on the left, the one-in clump is going to move very much further away. Oh, oops, sorry, I'm not, it's not my laptop, so I'm not controlling everything. All right, so you can see that the one-in clump has moved a lot here, while here it's still attached to the resonance. And so one reason that we formulate for that is actually the radial electric field that is generated by the zonal flow is creating a shearing rate that counteracts the downtripping of the mode frequency, that forces the mode here to stay in that position. And so as it does, so like it allows less particles to be resonant with the mode, as you can see here. And so that it reduces the kinetic drive of instability and in total lowering the saturation amplitude. So to conclude the validation, so I'm just going to compare the tripping rate obtained between the experiments and some simulation. So in green, you have MCDC1, in red, you have GTC, and in blue, the experiments. So you can see, first of all, that the fishbone burst duration is much shorter in the simulation than in the experiments, by a factor of 10, 20, and that the down chirping is also much faster in simulation by factor of 4 to 10. And we think that this is due to lower dissipation because we don't have a multi-scale approach. We don't have a lot of different N harmonics for N modes. So, for example, you can see that the chirping is much lower in CDC1. We think because we include also the N equal 2. And we hope that we will be able to recover the correct chirping rate by also including toroidal mode numbers that can be associated either to Alvan modes or to microturbulence. So that will be the subject of Tuesday talk by Xiang Lin. So now that we have validated GTC in the non-linear phase, so yes.
Do you have some measure of numerical distribution?
Actually, I don't have the. And so yeah, so now that the validation has been done for GTC in the non-linear phase, we look at the prediction for the EP transport in here. So starting with the linear stability of the case that was given to us. So again, similar to the DCVD case, we can see that when we use Maxwellian distribution for fast ions, the mode are stable. But as soon as we use a realistic beam for fast ion, we can see that we trigger fishbone mode past a given threshold in beta for fast ion. And that the mode structure again is a strong N equal 1, but with a significant N-2 side similar to this 3D. And so in terms of linear resonances during the mode, so for that case, we have very few trap particles, so it's mostly passing particles. Here you have the distribution. And so we have two different resonances that are driving the mode with the main resonance here. So those two are of drift transit type. Now let's look at what's going on at saturation. So similar to the D3D case. So when the mode is saturating, you can see clearly a downshaping of the mode frequency that is dominant. But in addition to for that case, you can also see an upshaping here. And so contrary to the D3D case, the mode saturates the relatively low amplitude without the zonal flow of the order delta V over B 10 to the minus 4. And again, the zonal flow inclusion lowers significantly the saturation amplitude by a factor of 4. And so what is causing, again, saturation here is the EP transport. So, but to the different distributed case. For that case, we have both inward and outward BP fluxes. So here you can see the perturbed density profile as a function of time. So you can see that so we have three different extrema for the gradient of the pressures that leads to here an outward transport for that line and for that line, and to an inward one here. And so those two outward and inward fluxes actually lead to a very weak distribution that is only about 0.15% of the initial density profile, which is extremely low and actually quite satisfying for ITER operation. And the reason for that is actually because the NBI pressure drive is much too low to cause any kind of large distribution, because it's mostly flat within the Q volume. So to finish off with this analysis, I'm just going to describe also what happened in phase space for that transport. So again, similar to the distributed case, we do have an income forming around each of the resonances. So as you can see on the amplitude here, so the amplitude is like normalized by the maximal amplitude for the initial distribution. So it only affects 0.02% of the initial distribution, which means that the fission-induced heat transport should not be problematic at all for the ITER scenario, at least only for the fission instability. So as a conclusion, so we have the GTC code has been verified and validated for King instability in the ideal MHD limit. So we have found that both the ITER and the discharge were fission unstable for realistic NBI distribution with similar mode structure, that the inclusion of zonal flow actually significantly lowers the saturation amplitude and lead to precise validation with the EC measurement, and that the zonal flow actually prevents the income to move in phase space that reduce the amount of resonant fast particles that can interact, and hence lowers the fission saturation. And finally, we have found that the transport by fission in the ITER scenario is very small due to the weak kinetic drive found from the NBI beam, quite actually significant for the discharge without the flow. Thank you for your attention.
The first about the benchmarks, you said channel shift is very important to cover the.
Yes. So actually, we didn't make any attempt at studying numerically like how it evolves. So what we did is we just like use directly the result from cheese to be able to recover the channel shift. But we were able to see that any like a 10% modification in the position here of the twin surface was sufficient to increase by factor of 3 the growth rate. So I would expect the Gaussian channel shift to be essential. Yeah.
The spatial distribution of and here you look at what also in the sense of two only
right.
At the feedback or somehow you have a temporal separation experience so that you can get the feedback of the energy from the structure.
So actually, the structure of the nerve flow hardly changes during the simulation. So I'm not sure like they have a significant contribution to it. I think like it's mostly the other way. That's mostly the nerve flow that.
But why is it so? Is it because it's built to work, or because you want too short time scales, or?
I think so. Like it is inside GTC, just like the simulation here are not done for a very long time. So I'd like to be able to simulate longer simulation to be able to potentially see that. The issue also is that we have some issues with some numerical instability that get triggered at 0.3 milliseconds or so. So like we need to fix that first. But yeah, for the moment we don't see any interaction of EPs on the node itself.
Possibly, if you were to move to where you need to relax what's a constraint in GTC and have the possibility of also something like that.
So we do have a feedback. Like the zonal flow is computed in GTC using the zonal densities of all of the species in there. So like we essentially it is contained in the formation, just that doesn't seem to appear significant. At least for those time scales.
You have somewhere a gradient, a phase gradient, things like that. were to relax that, you feel that on the temporal scale that you are interested in, it could have an effect?
I'm not sure what you mean by I have a fixed gradient in the simulation.
Well,
I mean, I don't have any fixed pressure gradient in that. So I relax all of the gradients in that case. So that's why actually you can see the transport. That's why you can see the particle being transported. So like we have the option to fix the gradient, but like this was not done in for the simulation. Yes.
that's time scale.
Right.
This may not be a fair question to you. I mean, this is scientifically interesting term, but I think we are in a country where ITER is being built, and I see some D3D people around here. So around 4 years ago, I hear when D3D did ITER baseline scenario IBS, the threat was Turing mode, low mode number Turing movement, plasma don't rotate.
All right.
But it seems ITER organization has chosen shots which is Turing mode stable. So, you know, anyone knows the story regarding the Turing mode no longer a threat to ITER?
I think it is.
Yeah.
But that was carefully chosen.
So-
particular shot.
So like here we're working with the EP group at ITER. So like they were mostly
EP groups. So
Yeah. So like we were mostly
Yeah.
Yeah. So like obviously Turing mode is an issue, but like so much so as the fast particle. So we have selected a like a right range of scenario, but like yes, that was mainly focused on.
Yeah, I learned the Turing mode when I was young, so I still think.
Okay.
There's another quote which is looking at controlling distances. So many groups. Just the last one.
Mhm.
Could you tell us more on the mechanism by which zonal flows are changing?
So for now, it's mainly an assessment. So there's two things. So like I do observe this kind of changes here. I'm going to show you again. So I do observe that without zonal flow, I do have a motion of an income that is due to the downtripping, so that we know. But on the contrary, with zonal flow, we don't have anything. So I'm formulating some kind of mechanism that could explain why I don't have this. And so like I'm currently still working on finding out the amplitude to see whether I'm correct. But my feeling is that potentially the ER field created by the zonal flow is creating a shearing rate that actually could counterbalance the downtrip. Like you create a omega E rotation that could basically like compensate for the drop of the mode frequency and explain why the rolling clump cannot move, because usually it moves because it stays attached to the resonance and moves with it. But
they're still jumping, right? On the right.
yes, they are tripping in both cases. That's why. That's why. And the reason why it doesn't move, you should have something that is counterbalancing the downtripping. And the only my main idea is that is that the regular electric field. But I need to compute quantitatively the shearing rate to be sure that it's the same order of magnitude and that can influence back. But given how this doesn't move, this move, I think that could be a fair assumption.
Questions? I think in Centurion.